Hi, in this video, I'm going to give a summary of Chapter 5 of the Deep Learning with Python book from Francois Chollet. This book is in the references of this video, and the chapter is called Deep Learning for Computer Vision, and it's basically about convolutional neural networks, which is the preferred method for computer vision applications and image processing. Okay, so here's the outline of the chapter. First, we're going to go through understanding the convolutional neural networks, then we're going to use data augmentation to mitigate overfitting. Then we're going to use a pre-trained COBNet to do feature extraction. Finally, going through fine-tuning and visualization. I'm going to go through, in this video, I'm going to go through a theory, but I'm going to refer to additional videos that go through the actual examples in Python. These videos are in the references of this video. Okay, so the chapter basically, again, mentioning that convolutional neural networks are are the way to go for computer vision and image processing applications. And we usually work with small training sets on like large companies. And the first example is this one. You can see it in the references as a separate video, and it's gonna use a very simple convolutional neural network to detect digits in images. Convolutional layers are very popular, like dense layers. These are two of the most popular. In dense layers, they can be seen as a matrix multiplication, in which you have a huge weight matrix that is multiplied by the inputs, the output of the previous layer, and they can be used for classification. And they also call fully connected layers. And basically, you have a weight for each of the connection. Everything is connected. For convolution, it is cheaper because it's like a sliding window. Imagine that this is your input matrix, and you slide this window throughout the whole image. It's going to detect patterns like edges, textures, and so on. It's going to do something similar to what image processing, morphology, or ion filter, things like that do. And the kernel can be a size of 3 by 3, and it's easier to train because you have a smaller weight. So in terms of memory, it's cheaper as well, and it's going to detect local patterns. One of the properties of the convolutional networks is that they're translation invariant. For example, since you have a sliding window going through the whole image, for example, if you want to detect an ear of a panda, the sliding window is gonna detect the edge for it anywhere because it's sliding throughout the window. And also, the max pooling helps in that, I think. And also, if you have a stack of layers, they increasingly detect more abstract patterns. Like in here, you can see that the first layers detect edges, textures, and then eventually you start to detecting eyes, ears, and it is hierarchical. And translation translation invariant is important because, for example, you want to detect a cat in an image, the cat can be anywhere in the image. The author is trying to clarify that the inputs for the CNN are tensor 3D tensors that represent the height, the width of the image, as well as the channel, which represents usually the color red, green, blue, which has 3 elements, but you can have more than 3 elements in an hyperspectral image. And the output is not the color, it's another tensor, but doesn't represent the color, but filters that represent features. You're encoding features, and those features become more abstract as the layers get deeper into the network. Okay, in this slide, it is restating what it was said before, that we have a feature map and that encodes the features, and you can see this as the initial layers of the convolutional neural network as like image processing filters, generic ones. Yeah. The two most important parameters for the convolution layer are the output depth, which is the number of features, and the kernel window's height and width. Usually they are 3 by 3 or 5 by 5. Okay, here's an example of how the convolution works. Basically, it's like a sliding window that goes through the whole input image. Try to see this in 2 dimensions for now. So let's say, for example, we have a 3 by 3 kernel window, and we slide it throughout the whole image. We start here because we don't have padding and we cannot go out of bounds. So we start here, we take the neighbor pixels and multiply it by another matrix, which is 3 by 3, that has the same size, and that's the weight matrix. Notice that it is small, that's why it's computation doesn't have much memory, it's easy to train, and that's the weight matrix that you train for each layer in the convolutional network. It's not shown in here, but this 3 by 3 matrix is multiplied, and when you multiply, you have the let's say it's a scalar, the output. Here it shows a vector because you have the depth, but if you have a 2-dimension, it's going to be a scalar, and then the scalar is placed here, only one scalar. And then you go for the next one, take the neighbors here, multiply by a 3 by 3 matrix, and you get another scalar, and that's the value here. And then you keep going here, get the neighbors, and you get the value for here. Then you go down here, get the neighbors, multiply by the weight matrix, and you get the value for here. And you go on until you get the values for all of these. So all of these values are going to be this. So notice that since we don't have padding, we lost the borders, and that's why you have a 5 by 5, but then you have to subtract the top, the bottom, the left, and the right, and you have a 3 by 3 now. If you add padding, the zeros or any other value around, then this will be 5 by 5. We don't lose the size. Okay, but this image is 3-dimensional, so you have to consider the input size, and the output size is going to be different because the output depth is going to be the weights. And then of course you compute this computation for each iteration, and then you concatenate to form the output tensor. Okay, as mentioned before, the size can vary between the input and the output. If you have padding, it could be the same, and depending on how you do the padding, the size could be different. But the usual padding means that the input and output size are going to be the same. No padding means you lose the borders, like in this example. And also, if you have strides, the size is going to be different. In this case, that we just showed, the stride is 1. So you go from 1, 2, 1, 2. But if you have a stride of 2, you can jump from here to here. And now the size of this is going to be, you're going to lose additional elements. And actually, the max pooling has usually a stride of 2. A 2 by 2 stride, and that's why the image is reduced by a half for each max pooling layer, and that's good because you're trying to downsample the image to eventually go to the features. You're gonna want to reduce encode it. You want to reduce the size. But therefore, there's some applications like GANs that they do not want sparsity. That introduces the max pooling, and they prefer to have the stride within the convolution. So instead of using max pooling, they add stride to the convolution, but usually the stride of the convolution is 1. Okay, in the previous example, we lost the borders because we did not have padding. So we had a 5 by 5 image, and we basically lost the border. And the conv2d layer from Keras have a couple of options: valid and save. Valid is the option that we used before, that is going to go to the valid values. So in this case, we have a 5 by 5 image, and the output values, the valid values are these in gray because they don't go out of bounds. If we use this one, we will go out of bounds. Okay, so the other one is same, which means that padding is going to be added in such a way that the output height and width are the same as the input. So in here, we have an input image, and we pad values with 0 or repeating the values at the borders or other value. Okay, so now we can go through the borders because we don't go out of bounds anymore, and we keep the size. These options are similar to the ones that the GPU coder stencil kernel function has for the Matlab deep GPU coder toolbox. Yeah, so probably in Matlab you might have some similar options. And it's curious because the GPU coder stencil kernel function implements the sliding window pattern. So this convolution function can be done very efficiently with that stencil kernel function from Matlab. Here's an illustration of the strides, of how the strides work in convolution. So a stride is basically a jump. So let's say, for example, we have a stride of 2 by 2. So the iteration goes from here to here to here and to here. And notice that by doing so, the output is going to be downsampled. So instead of having a 3 by 3, we're going to have a 2 by 2. Okay, so the author mentions that this is unlikely. Usually, the first for the conv2 layer, the default stride is 1. So usually that's how we want it, and we follow the convolution by a max pooling. And as mentioned before, cases like GANs, you might use strided convolution rather than using max pooling to avoid sparsity. Okay, so we talked about a convolution already. Now we're going to talk about max pooling. As mentioned before, a convolutional layer is usually accompanied by a tree of the actual convolution, the rectified linear unit, and the max and the pooling. Okay, so the pooling is used to downsample an image, as it can be seen in this convolutional neural network image. So, for example, if we want to detect a car, we have an input image, a very big one, and we reduce the tensor size as we add and detect features, and eventually we flatten the feature vector, the tensor into a vector, do the fully connected dense layer, and do the classification to detect a car, truck, van, etc. Okay, so in order to get from this large image to here, we have to reduce the size, do an encoding. Some people call it encoding. This is for the case of classification. For the case of semantic segmentation, you will have to decode it back to original size to put the classification pixels into the segmented image, but that's another story. Still, in that case, the max pooling is used to reduce the size to do the encoding. Okay, so the pooling is similar to the convolution in the sense that it's like a sliding window operation. So the output of the pooling is going to depend on the neighbors. It's not shown here, but it's better shown here. I'm going to go there in a moment. So it's going to take the neighbors and do an operation. And the operation can be like average or max. For example, in this case, we're taking the max. Which could be called which is called a max pooling, which is the most popular type of pooling, the one that has been found most effective. So the author mentions that usually the max pooling has a configuration of a 2x2 window with a stride of 2. So let's say in this example it's exactly that. So you have a window 2x2, and then you make a jump of 2. Unlike if you have a stride of 1, instead of going from here to here, you will go from here to here. But now by doing this jump with a stride equal to the size of the window, you're making this look like a partition. Okay, so for the first window 2x2, the maximum is 4, so you have 4. Then go to the next window, the maximum is 8, you got 8. Next one is 6, 6, and 9. Okay, so notice how this broke the image size to half, and that's precisely what the max pooling does. It's gonna bring down the image size to half. And also, what by taking the max, let's say that you have it helps with the translation, translation invariant property. Because, for example, let's say, okay, this layer is, let's say that instead of numbers is 0 and 1, where 1 means that the gate got, I mean, the output got activated, and 0 means that it didn't. And let's say that this detected, let's say, a pattern, but this one didn't in one occasion. Then you take the maximum, you have 1. But then let's say that in order the object gets translated, and this one is the one that detects it. So now it's gonna still be 1. So in that sense, it's translation invariant, and I think Goodfellow mentions that it makes it a rotation invariant as well. But still, it can be seen as collecting features, collecting detected patterns between the convolution windows. Okay, why not? Why have to downsample the feature maps in this way? Why we cannot remove them? So let's do this. The experiment. The author does the experiment by removing the max pooling layers, and you can notice in the summary that the image size remained the same, but also the number of parameters increased drastically. So you might guess that the training time also increases, and the size of the model as well. Okay, so the author mentioned a few problems with this. The biggest one is that when we want to detect an object in an image, it's not just detecting local patterns. So if there's no max pooling, the convolution is going to do everything local. So, for example, if you want to detect the face of a cat, you want to know the ear is in one place, the mouth is in another place, so you want to detect this globally. And so basically, if the max pooling are able to downsample and collect and connect the things together and find this global information. Okay, so another problem is that the number I've mentioned before, the number of parameters is very large, so this could result in intense overfitting. So in summary, the importance of the max pooling layer is to detect global features and also to reduce the number of parameters in the model. And this can also be achieved by using strides in the convolution, although usually max pooling is the preferred way to doing so. Also, it can be done with average pooling, but it has been found that max pooling is one of the most effective methods. Okay, so here we have the max pooling back again with a window of 2 by 2, and also the author mentions that and you can see the summary how the size of the image gets reduced by half each time it goes through a max pooling layer. And also the author mentions that having this max pooling is like making connection. For example, if a convolution layer detects edges, then doing this connection is like detecting a shape. And also as the network goes deeper, it can also be seen as a hierarchical collection of information. Perhaps like you can see in the cat that you have ears or the composition of patterns to finally detect a given object. As mentioned before, we're gonna deal with a small data set, which is the most common case for people that are trying to use deep learning that are not big companies. And we're gonna use a data set of 4,000 pictures of cats and dogs, 2,000 cats, 2,000 dogs. They're gonna be in the corresponding folder. So the folder is gonna be used to write the label, whether it is cat or dog. That's gonna be the expected output, which is gonna be used for training the neural network. 2,000 pictures of the 4,000 are gonna be used for training, 1,000 for validation, and 1,000 for testing. Okay, so we're gonna start naively without regularization to get, and we're gonna get 71%, and we're gonna get overfitting, and to overcome that, we're gonna use data augmentation. Okay, the author goes through a couple of examples. One of them is doing a convolutional neural network from the scratch. There's a video link in the references for that, and the other example is training fine-tuning a pre-trained network for the particular example that we're trying to tackle, which is the detecting cats and dogs. So that also is in the reference videos as well, that example. Of course, most of the cases you might imagine that using a pre-trained network is more convenient, more accurate, and more time efficient for training. Okay, in here the author is basically stating something similar, that the pre-trained convolutional neural networks are more convenient. And also one detail is that when you go from I'm gonna show an image. Okay, this is the image. When you go from an image into a classification, the initial layers, well, this is a simplified picture, but you're gonna have a bunch of layers. The initial layers are gonna take things, local patterns, generate things like edges, textures. So the initial layers are more close to the input, to the image, and the output layers, like these ones, are closer to the classification. So many of these initial layers are very generic, and you can reuse in many different classification problems. For example, in this case, you're trying to detect car, trucks, vans. For example, if you want to detect animals or something like that, you can reuse this initial layer. So you can take something like a pre-trained Imagenet layer and freeze the upper layers and retrain the lower layers. Replace the classification layer by your own vector dense layer, and basically you just fine tune it and train it only for the downstream layers to get your classification problem solved. Okay, so for the example that Francois Chollet is using that are referenced in the videos, are in the reference of this video, he's using this cats and dogs data set from Kaggle competition. Kaggle is a website that has deep learning competition, which the author highly recommends. And he says that this competition have been won by cognates which have shown to be very effective, and yeah, some details about the data from there. Okay, here are some of the recommended activation for the last layer of a neural network and the corresponding loss function. So let's say for this example that for cats and dogs classification, the output is a boolean. So you can it is recommended to use a binary cross entropy with sigmoid activation if instead you have a multi-class single label, which could be the MNIST digit classification example, which the output value is between 0 and 9. Then in that case, softmax is the activation, recommended activation, and categorical cross entropy. If you have multiple labels and with multi-class, then sigmoid and binary cross entropy. If the output of the neural network is a number, a real number, then that is a regression. In that case, you don't need an activation layer, and it is recommended to use mean square error. If the value of the number is between 0 and 1, it could be seen as a binary. So you can use binary cross entropy along or a mean square error, and sigmoid as the activation, I guess, to keep it between 0 and 1. The second example is detecting cats and dogs using a convolutional neural network built from the scratch. This is the name of the video, which is in the references. So I'm gonna talk about details about this example in the following slides. Okay, here's a snapshot of the convolutional neural network that we're gonna be was built from the scratch for the previous example in the reference that I gave, that is in the reference of this video. Unlike the second example, the network built from scratch, unlike the first example, it has an additional layer, and the additional layer not only increases the capacity of the model but also reduces the size before the classification layer. So notice that the image starts at 148 by 148, and it goes down by exponent divided by 2 and keeps dividing the second layer, and eventually ends up being 7 by 7 because it has 3 layers. Okay, actually it's 4. Anyway, it goes down to very little, but while the size of the image, if it can be called image because it's a feature tensor, but the height and width it gets reduced while the features gets increased. So you're encoding it into a feature. Finally, you just flatten it and go to the dense layer. So this pattern of increasing the features while reducing the height and width is very common in convolutional neural networks. When working with deep learning networks, there's significant amount of work done in pre-processing the data to make it a tensor data that is that can fit into a network. And this, of course, is the case for image processing and computer vision applications for convolutional neural networks. So one of the things is that the neural network expect a floating point tensor, and it is more convenient to have the value between 0 and 1. It's good to decode the JPEG into RGB if you have a JPEG. And there are other conversions that you might have to do, but those are the most important. And Keras has the image data generator class that helps you to do this automatically. And in the case of Matlab, you have image data stores that do exactly the same, or more or less better, perhaps. Okay, I mentioned image generator from Keras, but what is a generator? That is a Python concept, and it depends on the keyword yield, which is like a return, but it pauses the execution so that it can continue on the next code. So for example, you can use the generator as an iterator, and when you call it like this, it's gonna call the function, it's gonna go inside, compute this I becomes 1, it's going to return 1. It behaves like a return. You get the value, you print it, and then you go for the next cycle, call the generator again, but instead of going from the start, it's going to go from the place where it stopped last time, where it yielded. So it's going to go again to the loop, it's going to increment to 2, it's going to return 2, and you're going to get a 2 in here. So that's how a generator works. Okay, the Keras deep learning model libraries have a fit generator method, has a fit generator method that expects a generator as an argument, so it's ready to handle generators. Similar to in Matlab, when you train a model, it can expect a data store as an input. So this generator or data store, in the case of Matlab, fetches data one at a time, but you also can indicate the batch size. So you can have more than one sample at a time. And also, like the data stores in Matlab, the generator can generate data, infinite data. So you have to tell it when to stop, because otherwise it doesn't. One of the biggest problems in training neural networks is overfitting, and especially when you have a small amount of data. And here is an example of how overfitting works, and you can see that in the second example from the references. Basically, you provide a training data, and the neural network is going to be over calibrated to fit that training data, so you can get close to 100% accuracy. But while the validation gets stalled at 70% accuracy. Okay, so ideally, you don't want this to be so high. It's better to have the validation as close as possible to the training, because it means that it's generalizing well. And there are some strategies to avoid overfitting. One of them is to use dropouts, which is like I think they may call it bagging. It's like having multiple methods, multiple models in the same model, and usually the dropout appear next to the or before the last fully connected layer. It makes sense. It makes more sense to put it in the dense layer, because you have a bunch of connections. The dense layer, everything is connected. So you basically, what dropout does is randomly break connections in each epoch differently. So it's like having multiple different models in each epoch. So you train different weights for each epoch. But this doesn't make sense in convolution, because convolution is such a small amount of connections that it could be problematic. So another technique for countering overfitting is doing data augmentation. In the case of image, that could be in the case of computer vision image processing application, it could be things like inserting noise or doing fine transformations like rotation, translation, shearing, and all these things. Not only is good for fighting overfitting, but it's good to make it the convolutional neural network more robust, because when you apply it in real life, you're gonna get noise, you're gonna get the fine transformation. So it's better to get it ready for that. The problem of overfitting stems from having a small amount of samples to train the neural network. If the author mentions that if you have infinite amount of data, then it will never overfit, because your training set is the whole universe, so it's gonna always predict well. Well, since we usually have a small amount of data, it is good to use data augmentation to augment the amount of images that we have. For example, if we have a 4,000 images of cats and dogs, then we just apply noise, rotate, shear, shift, translate, all these combinations of fine transformations, and we're gonna have a high probability of creating unique images, and that is gonna fight not only fight overfitting, but make it robust toward those transformations which are expected in real life anyway. Okay, for the cat and dog classification convolutional neural network example in the references, the image data generator is used. Here are some of the options for the affine transformations, which includes rotation range, the shift range, the shear, zooming, horizontal flip. It might also have a vertical flip. And sometimes usually when you rotate an image, some of the pixels get out of the screen and some other pixels are left blank, so you have to decide how to fill those pixels. In the previous example, we detected cats and dogs from images using a convolutional neural network created from the scratch. And in this third example, the same problem is going to be done, but using a pre-trained convolutional neural network. So this example is, there's a video for it as well, which is in the references of this video. And in the next slide, we're going to talk about this third example. Using a pre-trained neural network can be convenient when data is scarce. One example is Imagenet, which is trained with many images, and it is trained to classify animals and every day objects, but also can be repurposed to train things as remote as furniture items. And this is one of the key advantages of deep learning: the ability to reuse pre-trained networks and layers. And for convolutional neural networks, you can see, as in this example, that the input layers are closer to the image and the output are closer to the classification. So you may expect that the output backend layers are closer to the objects, and those are the ones that you have to retrain or replace, especially the classification one. But the front end one, which deals with edges and geometrical properties, they are common, and you might choose to take a pre-trained model like Imagenet and just freeze them and train the rest. Okay, for the pre-trained neural network example, we used the VG16 architecture, which uses the Imagenet dataset, which has 1.4 million labeled images and 1,000 different classes, and contain many animal classes, which make it good for the example. And it's far from the state of the art, but it's easy to understand. And here are some examples of other pre-trained neural networks that can be used for computer vision. And there are two ways of using pre-trained neural networks: feature extraction and fine-tuning. And we're going to talk about the first now. Feature extraction consists of using the front-end layers from previously trained networks. And here's an example that we have a network that is already trained, like the one that we're loading in the third example. And we just remove the classifier, which you expect to see dense layers here, fully connected layers, and in here you expect to see the trio of convolution, max pooling, and ReLU. And it's not exactly like that, but it's somewhat like that. And once you get rid of it, you put your new densely connected layers with the number of classification features in here, and retrain it again with this one. You might freeze this, or you might freeze some of them. It's up to you. As mentioned before, the front layers are more generic and closer to the input. They represent things like edges, colors, textures. They're closer to perception, and they can be used for different classification problems, while the latter layers contain things like cat, ear, dog, eye, and they're closer to the actual object, and that may include some of these layers. So yeah, it's up to you to choose where to stop the training. And yeah, front end could be seen as closer to the input sensors, and while the backend closer to the output domain. These are some of the pre-trained models that are available in Keras, which you can also use in Matlab deep learning toolbox as well. Okay, the author mentions a couple of options to train the pre-trained convolutional neural network with your new classification layer at the end. One of them is to connect the new layer and train everything. And this is the most computationally expensive, but it's the most precise, and data augmentation works with it. But the other option is run the pre-trained layers with the data set and store the output in a local disk, and then independently train the classification, the rest of the network with the output data of the network, and this in terms of computation is cheaper. The option to train the full neural network given a new classifier is very costly, and if you don't have a GPU, it's not recommended. And yeah, especially when you use a pre-trained neural network, it has a bunch of parameters which can make it very heavy on practical. And here you see a summary of the pre-trained neural network glued together with the new fully connected layers for the fitting it to the classification problem at hand, classification between cats and dogs, which is a boolean at the end. So you can see here that we have almost 40 million parameters, and again, it's good to freeze the upper layers to make the training faster, and also you don't want to modify the generic layers because you don't need to. By freezing the base layers, you have only the dense layers to train, and the property that is used to configure that is the trainable properties, and you should see this in the third example in the references. And also a reminder that when you do these changes, you have to compile them all, otherwise they will not take effect. Another option is to train to use a pre-trained COBNET is to do fine-tuning. This is similar to the first option, which was the chip option, in which you leave the first layers alone. But in this case, you're gonna unfreeze some of the layers that are gonna be fine-tuned along with the classification layers, and keep all the other ones frozen. And you train this together. So still, it should be cheap and should be effective. So here's a suggestion of doing fine-tuning. First, add your custom network at the top, which is this one, and then freeze the base network and train it. And then after you train it, then unfreeze some of the layers, maybe these ones. The ones that are closer to output are the more abstract ones, and those are the ones that you're interested in retraining, not the generic ones, which are very abundant. And then train it again, and this should give you better results. Okay, so here are some of the takeaways of this presentation. COBNETs are the best type of machine learning model for computer vision tasks and image processing as well. It is possible to train one from the scratch on a very small data set. Also, it is possible to use a pre-trained network. On a small data set, overfitting would be the main issue. Data augmentation, which is basically apply things like noise, fine transformations, rotation, translation, shearing, zooming. Those are powerful It's a powerful way of fighting overfitting because it creates a bunch of images and also makes the neural network more robust in things that are important for computer vision. It is easy to reuse an existing COBNET on a data set via feature extraction. Feature extraction is the chip technique in which you take the outputs of the base layers and save them into a file, and then train the backend classification dense layers. As a complement to the feature extraction, you can use fine tuning, which was freezing the base layers and then train the classification, and then freeze a layer of the near to the backend convolution layers to do additional training, and that should push the performance a little bit further. And this should be a good set of tools for dealing with image processing, computer vision, deep learning problems with small data sets. Thank you very much for your attention.